All right, so the problem of writing or constructing the automorphisms of R3. So again, what are the automorphisms? Depending on which terms you want to use, the linear maps or the isomorphisms of R3 onto itself. And when you think about it, you think, what would the obvious ones be? The dilations and contractions are the easiest ones to think about. I think we already did that. But as soon as you get to the rotations, it's not even as clear as it is in R2 what you mean by rotation. So let's start with the simple examples, or the simplest ones maybe would be the rotations about the the coordinate axes. So rotations about the x-axis, y-axis, z-axis. And then you'll see how basically once we get that done, it'll take care of everything else. It will. So let's start off and suppose we want to rotate about the x-axis. There's x, y, and z. We want to rotate about the x-axis by some number of degrees. Well, let's see. How on earth would we do such a thing as that? Well, remember, a nice thing is if we know what a linear transformation does to the basis vectors, then we can immediately write down what that transformation is. So what we want to do is figure out what this rotation does to the basis vectors, and then we can write a matrix which will achieve that transformation. Well, what happens to this basis vector, e sub 1, the basis vector coming out here, a unit of 1? There's e sub 1 right there. Well, nothing. So let me see if I can get my eternal quest to getting more things right better. So maybe I'll make a note over here. The rotation, in terms of trying to find the rotation about the x-axis, let's develop a little notation here. Maybe nothing standard about this. This of E1 is E1, so it leaves that basis vector alone. What about Y? Oh, so here's E2. Here's E2. And we want to rotate this. Now, this could be an important thing if I say rotate it through a certain number of radians. In what direction do we rotate it? It really could be any. It's really up to us to decide. And we will have to think about the ramifications of this down the road. But let's take what I think is the obvious approach. Let's rotate this towards the positive z-axis. We don't have to do this at all, but let's go ahead and do that. Now, if I do that, let's say, for example, E wound up here. Now, you have to imagine that that is moving in the y-z plane because we're rotating about the x-axis. And we would have rotated it theta degrees. Well, what we really have here is a two-dimensional rotation. Now, we did this before, but I don't have the formulas in front of me, so let's see if we can knock this off pretty quickly. If this was e sub 2 right here, remember, magnitude of 1, and we rotate it through an angle theta. So here's, well, at least the magnitude of e sub 2, which is 1. Right here, there's theta. We've got a nice right triangle. That's pretty straightforward. So remember, on this picture here, translated down here, here's the y-axis, here's the z-axis. What is this distance right here? Cosine theta. What is this distance right here? Sine theta. So that tells us what this rotation about the x-axis of E2 is. It'll give us the vector. Remember, what happens to x? X stays the same. What is the x-coordinate? E sub 2 is 0, so this is 0. The y-coordinate, I think I just said it a second ago, is cosine theta, and the z-coordinate is sine theta. And let's get the rotation. The rotation about the x-axis of theta degrees of e sub 3. We're going to do a similar sort of thing. Again, I got to be a little bit careful how I draw the picture here, but here's e sub 3 right there, e sub 3. Unit basis vector in the z direction. We're rotating about the x-axis, so we wind up with a vector here. I think I can use this picture as it stands right there. There's theta. Remember, that rotation would occur in the y-z plane. Now, how do I write the coordinates here of this? Actually, let me, instead of doing it there, maybe let's form the triangle here like that. There's theta. Sorry, there's theta. What is this length right here? It's sine of theta, but it's in the negative direction. So that's negative sine of theta. So negative sine of theta, that's right there. And then this right here is cosine of theta. So what happens here, again, this stays 0 because we're rotating about the x-axis, and it's E3, the unit basis vector, in the z direction. So x stays the same, and it was 0 to begin with. And the y-coordinate here is negative sine of theta, and this is cosine of theta. So this tells me what the rotation about the x-axis does. Now, how can we write a matrix? Remember, one way to get the matrix which performs a particular linear transformation is to write where the unit basis vectors go as the columns of a 3x3 matrix. So R sub x, basically we can write it like this. This is where E sub 1 goes, this is where E sub 2 goes, this is where E sub 3 goes. E sub 1 stays itself, so 1, 0, 0. Where does E sub 2 go? Right here, so 0, cosine theta, sine theta, and here is where E sub 3 winds up being mapped to. 0, negative sine of theta, cosine theta. Okay, now how should I really denote this? Well, this is R sub x of, wow, this notation can be kind of awkward here, and I'll show you what I mean. What is the argument for this? What is the argument for this map? It's a point in R3. What does a point in R3 look like? Well, it looks like x, y, z. You see, it's kind of awkward because I mean the rotation about the x-axis. This x and this x really symbolically are not actually the same thing. I suppose one thing we could do is we could just do something that we've done all the way along, is do something like, say, v. Think of that as a vector. This is probably better right here. How do we rotate this vector about the x-axis? We multiply it by this matrix, right? So if we have a vector v, it would have the 3 coordinates. We write it here and do matrix multiplication. So this is the matrix that gives us rotation. So here I should actually do something like put a v here like that. Actually I should do what? Because that's a vector and I need to write it as a matrix. So a vector is not technically a matrix. What might be, I mean, that's probably clear to write it like that, honestly. I could do something like this to emphasize the fact that we're doing matrix multiplication. So there's the rotation about the x-axis. Now we can do this, we want to do the same thing for y and z. So let me do it for y, and then I'll let you do it for z. You can do the same thing for z. Here, I'll erase this picture. Hopefully I can just a little bit quicker now. Maybe not. Okay, so now let's rotate about the y-axis. There's x, as always. X, y, z. We want to rotate about the y-axis by an angle theta. How do we determine the overall transformation? We want to find where remember, like I said before, the unit basis vectors go. Well, right away, E sub 2 just stays E sub 2. So the rotation about the y-axis of E sub 2 is E sub 2. So that's easy enough. Now, again, let's do x. And let's figure out what the rotation about the y-axis of, x, I mean E sub 1. Which way do I want to rotate this? Again, I do want to make a note of this somewhere. For example, over here, somewhere along the way here, we should make a note that when we've rotated about the x-axis, the y-axis has been rotated in the direction of the z-axis. Now, one thing I may notice is if I, think about the right and the left-hand rule. Again, remember, I got to say this again. That was arbitrary. I didn't have to do that. If I rotate what we did a minute ago, we rotated about the x-axis. Y, I curl it up to z. x points out this way. That sort of seems to go along with a right-hand rule. Now, if I take, now what am I doing now? I'm rotating about the y-axis. So how maybe should I do this rotation? Well, if I come out the x-axis here and rotate towards the z-axis, I would get a left-hand rule. Nothing wrong with that. I'm not creating a coordinate system here. But maybe our first stab at this, just to keep things consistent, we want to stay with a right-hand coordinate system. So here's the x-axis coming out at you. If I curl my right hand towards the z-axis, then this would conform to being the y-axis. So let's take e sub 1 right here, and we'll rotate it in this sense, down here like this. So we get now that vector there is in the xz plane, and there's an angle of theta. So if I were to translate this drawing down here, what would the drawing look like? Here's z, here's x, here's e sub 1, and we rotate it through an angle theta. Well, what changes here? The x and the z coordinate changes, right? And let's see if we can draw a picture here like this. What is this amount right here? This is cosine theta. So the new x coordinate after the transformation is cosine theta. This is sine theta, but it's down in this direction, so it's negative sine theta. So here I can, over here I use this diamond bracket notation, but just because I don't have room here, I'll write it like this. So what happens to the x coordinate? We get cosine theta. The y coordinate stays the same. So that's 0. Again, look, this was e sub 1. What are the coordinates of e sub 1? 1, 0, 0. We rotate about the y-axis. The y coordinate stays the same. So that's still 0. And what do we have here? Negative sine theta. Negative sine theta. So that's what it does to e sub 1. Now all we have to do is figure out the rotation about the y-axis of the unit basis vector e sub j. Sorry, 3. I was thinking of ijk, but we use 3 here because we decided to in linear algebra. So let's see, we're rotating about the y-axis. We want to see what happens to e sub 3, the unit basis vector in the z direction. Now here we have, if we're going to rotate this way, of course, this has to come down like this. We don't seem to have a choice there. I just want to make sure when I did the x-axis a minute ago that I did a similar thing. Yeah, we did. Okay. So this would come down here to look like this. There's e sub 3. It rotates like that. There's theta. If I produce a different drawing to take a look at that right there, what would the drawing look like? There's z. There's x. There's e sub 3. There's that vector after its transformation. And there's theta. So what's the new x vector? The new x vector is negative sine theta. So negative sine theta. The y vector stays the same, 0. And what's the new z vector? Well, z is this, right? Z is this quantity right here, this magnitude right here. So that is cosine theta. So cosine theta. Okay, so let me write this down over here. Let's say the rotation about the y-axis of any vector v in R sub 3 is going to be given by the matrix. Again, the key thing here is this matrix. This really is the formalism. I mean, it's good to write it down, but this is the matrix which accomplishes the rotation about the x-axis. What's the matrix which accomplishes the rotation about the y-axis? Is, well, this is what happens to e sub 1. What happened to e sub 1? Cosine theta. 0, negative sine theta. What happens to e sub 2? That stays the same. So 0, 1, 0. And what about what happens to e sub 3? Negative sine theta, 0, cosine theta. And to be consistent with this, I'll do this. But the key thing here is the matrix. Please write these down. We don't want to ever have to rederive these. Here's a matrix which rotates R3 about the x-axis. This is the matrix which rotates R3 about the y-axis. And I'll leave it to you to do the z-axis. Maybe, or at least maybe we should discuss well, wait a minute, hold on a second. What direction do we want to rotate about the z-axis? And then I'll leave it to you. Because we did have to make this arbitrary decision that when we said make a rotation, what does that mean? And that's okay, because if we want to perform any given rotation, we could consider what our definition was. And then if somebody said, for example, rotate it this way a number of degrees, but our sense of orientation had been rotated this, we would just either make that rotation a negative number of degrees or 360 minus that number of degrees. So that's okay that we make this arbitrary choice. Now, what about rotating about the z-axis? Rotating about the z-axis. Here's z. In what direction should we do it? Well, let's see. Here's x. Curl towards y, and there's z. So yeah, it seems like what we should do is take, here's e sub 1, and we should rotate it in this sense, in the xy plane. So we get a vector right here, and there's our transformed e sub 1. Maybe I'll just pick that one off while I'm at it here. So what is the rotation about the z-axis of e sub 1? Well, let's see if we can just see what this is going to be. Here would be our right triangle like this. There's theta. Where's theta? Theta's right there. So this right here would be cosine of theta. And what about the new y-coordinate? The new y-coordinate would be this quantity here, so that would be sine theta, and this stays the same, so 0. And let me go ahead and finish this off here. The rotation about the z-axis of e sub 2. So e sub 2 is here. There's e sub 2. We rotate it in the xy plane right there. There's theta. What's the new, let's see, this is the new y-coordinate. When I say new y-coordinate, yeah, it's the y-coordinate of e sub 2 after the transformation. So what is this right here? That's cosine. So the new y-coordinate is cosine theta. What's the x-coordinate? Well, there's sine theta, but it's in the negative direction. So negative sine theta, and down here this is 0. And I didn't write it down, but r sub z of e sub 3 is e sub 3. So yeah, let me go ahead and write that down. Now we'll get them all. We'll have them all down. Have all the rotations down. So rotation about x, rotation about y, and finally here's rotation about z. Rotation about z of a vector v in R3 is given by the following matrix. Let's see, here's where our e sub 1 winds up. So cosine theta, sine theta, 0. Here's where e2 winds up. Negative sine theta, cosine theta. Cosine theta. Oh no, what did I just do? 0. Why does something not look right here? Well, I'll be able to find out in a second here. 0 and then 0, 0, 1. In checking these again, when you rotate about the x-axis, the x unit vector, the unit vector in the x direction should stay unchanged. So there it is right there vertically. There's e sub 2. There's e sub 3. And when I think about rotating about the x-axis, you rotate about the x-axis. If you rotate about the x-axis, the x-coordinate should remain unchanged. So there's the two x-coordinates right there. And here's the two z-coordinates here. Something doesn't look quite right. Here's the two y-coordinates. There's the y-coordinate, and there's the y-coordinate. So, sorry, something didn't look right to me, but it is right. So write these three matrices down. In the next video, what I want to show you is that basically once you've got these three, we can get all the tricky automorphisms of R3 onto itself. We can go over it again if you want, but the contractions and dilations are easy. You just multiply the magnitude by a constant. And I do want to talk about the idea of a shear. What is the analog in 3D to a shear and a flip? The shear is pretty easy. I'll show you the next video of that. That's pretty easy. The rotations and the flips seem difficult, but what I'm going to show you is once you've got these three, no problems. We get the other ones. Okay? So again, make sure you get this, and this copied down. And then in the next video, I'll show you with those three, we get everything that we want. And then you never have to do that again. So that's a good thing.